Hello everyone, welcome to the DSA practical series. So in this particular practical, we will be doing the simple microprocessor based programs showing us arithmetic and logic operations. So these are some of the first we will see the arithmetic instructions, then we will do the programs. So the first one is add R. All these instructions are with respect to 8085 microprocessor. So this add R, so R can be any register. So as we know, in case of 8085, the registers are A, B, C, D, E, H, L. These are the registers available. Now this add R, it is a 1 byte instruction. And what does it do? It adds the contents of register A with the given register, and it stores the result in register A. Okay. So suppose if we write add B, there is an example given, add B. So add B means what? The contents of register A are added with register B and they are stored in register A. Okay, so in fact add B means A equal to A plus B. Then add H. So add H means what? Add the contents of register A with register H and store the result in register A. So add H means A equal to A plus H. Okay. Then we have sub R. Sub R is also a 1 byte instruction. It subtracts the content of the given register from register A, okay, and stores the result in register A. So register A is a very important register in 8085. All the arithmetic, almost all the result of the arithmetic operations and logic operations are stored in register A. So sub C means what? Sub C, A equal to A minus C, okay, where A and C both are registers. And sub D means A equal to A minus D. Then we have INR and DCR. So INR means increment the content of register, given register. So this is actually even a 1 byte instruction. INR is a 1 byte instruction. It increments the contents of the given register by 1. So if we write INR B, it will increment the contents of register B. So suppose if register B contains 06, with INR B it will become 07. Similarly, INR C, we can increment the content of any register. Then we have DCR. Now DCR is, the meaning of DCR is decrement. So even this is a 1 byte instruction. It decrements the contents of the given register by 1. So we have DCRD means D equal to D minus 1. So if D contains suppose 07 and we give the instruction DCRD, it will become 06. So 7 minus 1 becomes 06. So these are the few arithmetic instructions. Then we'll see some logic instructions. So this is for the first one, ANAR. So ANA means logically AND. Okay. So what does it do? This is a 1 byte instruction. It logically ANDs the contents of register A with the given register and stores the result in register A. So ANAB means what? A equal to A and B. So this ANAB will AND the contents, logically AND the contents of register A with B and store the result in register A. Similarly, ANAH will do the same thing, A equal to A and H. Then ORA, as we have the AND operation, we also have the logically OR operation. And even in this case, when we do the ORA is again 1 byte instruction. So ORAB means what? A is equal to A or B. So it logically ORs the contents of A with B. Okay. So by default in most of the arithmetic logic operation, A is one of the default register. Okay. Then we have XOR. XOR is actually XOR operation. Okay. So XORAD means what? XOR the contents of register A with register D and store the result in register A. Okay. Same way we have XORAL. Then we have the last one. This is CMA, that is complement. Okay. So this is a 1 byte instruction and the operand is register A. Okay. We cannot complement the contents of any other register but only A. So if we give the instruction CMA, it logically complements, that is complements with what? Converting 0 to 1 and all ones to zeros and zeros to ones. That is the complement operation. So we can complement the contents of register A by using this instruction. Okay. Now let us see some programs, some simple programs. The first one, write a program to store 15H in register A, 19H in register B and add their contents. So we need to store this data 15H in A, 19H in register B, and we have to add their contents. So the first instruction is MVI A. This MVI will store 15H in register A. MVI B 19H will store the data 19H in B. Add B will add these two data and we will get the result. Now because this is a hexadecimal result, so we must add the contents using the hexadecimal addition. We may also get the alphabets A, B, C and so on, and then we will get the whole. So after this add B, the final result will be stored in register A. This is the second program. So write a program to store 25H in register C, A1H in register B, and add their contents and store the result in register D. So we need to store 25H in C, A1H in B, and then we have to add their contents, and the final result must be stored in register D. So the first instruction is MVIC 25H. So this is the hex code. You can copy from the we can get the hex code from the hex code paper, and in the simulator which we are using, this code will be automatically generated. So MVIC is 0E and 25H will come afterwards. MVIB 06A1, so we need to store A1 in register B. Then we have to perform this instruction because without register A we cannot add the data. So we cannot add the contents of C and B directly. So we need to transfer the contents from C to A. Okay, so C to A. So this will transfer the contents from register C to register A. Then we'll do add B. So add B will then add the contents of A, which is actually C. Okay, and it will add that and store the result in register A. And in the program it is mentioned we need to store the result in register D. So what we do is move D comma A, so it will transfer the contents of A to D and halt. Okay, so we will get the result in A as well as D. Then next one is write a program to store 15H in register A, 17 in register B, XOR their contents and store the result in register H. Okay, so this two instructions, first of all 15 in A, 17 in B. Then XOR A, we will XOR the contents of register A with B and store the result in register A. And finally we need to store the result in register H. So this is move H comma I, because the final result will by default is in register A, but here it is mentioned we need to store the final result in H. So this is store the result in H also. Okay, then next is write a program to store 18H in register A, 45 in register B, logically AND their contents and complement the result and store in register L. So first we store the data A and B in the respective registers. Then A and A, B will ensure that we are ending the data A with B and the result is in A. So we need to complement the result. So therefore we do the instruction CMA, and then the final result is stored in register L. So this is how we perform this particular. This is how we have written the practical. Okay, now we'll perform it on the simulator, Jubin simulator. So I have started the simulator, Jubin simulator. So first we will type the program. We need to store the data 15H in register A, 19 in register B, and add their content. The first program, if you see, so we'll type the first MVI space A. So this is 15H, so 15H. Then MVIB, that is we have MVIB is 19H. Okay, 19H, and then add, so add B space B, and then finally halt. Okay, so before executing a program I will just set up the memory. So setting the settings, in go in settings and set memory range. So we'll set the memory range from 8000. Okay, and then we can just after this we assemble this. We have written the code, we need to assemble the code. After assembling we have to start this location, we have to change to 8000. Okay, and then we will execute the entire program at a time. Okay, and we can click here for the register so you can see what output we are getting. Okay, so after running the program, okay, as you can see in register A we are having 2E. Okay, because when we add 15 with 19 using hexadecimal addition, the answer is 2E. Okay, I will show how we will get 2E. Okay, the answer is 2E. So this is the data we have, 15 and 19. We write in this binary from hexadecimal to binary notation. So 1 is 0001 and 5 is 0101. 19 is 0001 and 1001. Okay, so we add this, perform the binary addition. So 1 plus 1 0 carry 1, then this is 1, this is 1, this is 1, 1 plus 1 0 carry 1. So this result what we are getting is 0 0 1 0 and triple 0 1. So this is 2 and this is E. So that's how we get the answer 2E. Now let us do the second program. The second program is also of arithmetic type. So we do the third program. Okay. So in the third program we need to store 15H in register A, 17H in register B, XOR their contents and store the result in register H. So this is the first instruction, MVI A 15H, then MVI B 17H. The second instruction, then XOR AB is it XORs the contents of A with B and stores the result in register A, but we need to store the result in H also. So move H comma A. Okay, so it will store the contents from A to H, that is the result in H, and then finally hold. So because we have already set the memory location in the previous program, we don't need to set it again. So we assemble the code. After assembly we get this. Okay, so these are the hex code. Okay, and even the memory starting from this execute starting from 8000, we don't need to change this one. So now we execute. Okay, run all at a time. Okay, so this is the result. As you can see, is the content of A is XORed with B and the result is 0 2. As you can see here, 0 2, and we get the result in also in register H, that is 0 2. We are getting it also here. Okay, now let us verify the result. Is it 0 2? So these are the two data. A contains 1 5, that is 0 0 0 1 and 0 1 0 1. 17 is 0 0 0 1 and 0 1 1. Now we XOR these contents. So the rules for XOR is that the output is high when odd number of inputs are high. Okay, so for 1 1 we will get 0, and for 0 0 also we will get 0, and rest all we will get 1. So this is 1 1 is 0, then 0 1 is 1, and rest all are, because they are 1 1 is 0, 0 0 is 0, so we are getting this result. So the answer is 0 0 0 0 0 0 1 0. So this is 0 2. That's how we verify this result. So that's all for this particular session. You can try the other two on this particular simulator. So thanks for watching.